So I want to talk about the lab yesterday and how you got your data for that. When you had your mass of your crucible here, okay? You had the mass of the crucible and the ribbon. So if you subtract the crucible from this value here, you're going to have the mass of the ribbon, okay? This is the mass of your magnesium, okay? Then you heated it. You took the mass again after you heated it. And if you take the crucible from here away from this, you will have this value. Make sense? Now that value, this material, these contents are magnesium oxide. So you are going to be taking, for mass 1, you're going to be taking this guy right here, your magnesium, over your magnesium oxide. So this value right here divided by this value here will give you percent magnesium. So if I were to number these, like data point 1, 2, 3, 4, 5, I would take data point 3 and divide over data point 5. Does that make sense? What I'm trying to say there? Yes, Madison.
Wait, but why don't we subtract the mass of the crucible after eating by the one with the magnesium ribbon?
Because you want to know the mass of the contents in there. That's going to be your magnesium oxide. So when you were doing this, what happened was you took magnesium from the air. I'm sorry, magnesium strip. You took oxygen from the air and you created magnesium oxide. So if you want to see a balanced equation, that's what happened there. Okay. You know this from data point 3. You know this from data point 5 above. So if you want to know the percent magnesium in this guy, you're going to take your part, which is the magnesium, because you know that didn't change, and you're going to divide it by the whole, which is magnesium oxide. That's going to give you some percentage here. You're hoping that you're in the low 50s to mid-range to upper 60s. So anywhere from 60 to or 50 to 70 is where you're hoping that your percentage came in here. Okay. Then down here, you are going to take magnesium and oxygen, and you're going to do your inventory times what's on the periodic table for each of these, and you're going to come up with what those percentages should have been. Just like you did on the homework. That makes sense? Now, when you are doing number 3, your data analysis 1, this was your experiment. So this is your experimental. This should be your accepted. And remember, when you're doing percent error, it's accepted minus experimental, absolute value, divided by accepted, times 100. Remember how to do that? So you're going to take your accepted value for magnesium from number 2 above, experimental of magnesium from number 1 above, and divide it by number 2. Remember, when you get to the end of this line on your calculator, what do you hit? Equals, then hit your divide key and punch in this number. Report this to the tenths or hundredths place. I don't care. All right, next one. You have magnesium oxide. Some of this escaped the crucible. So if that happened, remember you've got part over the whole for this. If magnesium oxide escaped, which value here would be affected, the top or the bottom? The bottom. How would it be affected? Would that value go down or would it go up? It would go down. So if this number gets smaller, what's that going to do to your answer? That's what this question is asking. Then you do the same idea for down here. Magnesium reacted with something else. It's gone out into the world. Okay. How would that affect this answer? We have a couple of definitions. You can Google those. We talked about the starting mass here and the ending mass here. You need to explain what the difference is. And I explained that at the beginning of this discussion. So if you didn't catch that, you might want to go back and watch the video tonight again. This is asking how these relate. Remember, you cannot defy the laws of science. Okay, if it's a law, it's a steadfast law. So that should answer this question, and then you need to explain it. It seems like the law of conservation of mass has been disproven because your mass went up, but you need to think about what those components are. All right, same idea, number 6. This relates to that material. Chemical, physical change, what happened inside of there. You need 3 pieces of evidence. List a pure substance, a mixture in the lab, and then the difference between pure substances and mixtures. We talked about intensive and extensive properties. So what were those in the lab? And then what are the difference between those? And then you've got a density problem here as well. Okay. So this lab is due tomorrow before the test. The last day that it will be accepted is Tuesday, and that is 10/11. So this is the last day accepted for credit. Now, what did I say up here as far as expectations for this lab? For the conclusion, what does it say here? It says, we can get rid of the number part here because that was old school. Answers should be written using complete sentences, not sentence fragments. Okay. And so a person who hasn't seen the question can understand what you're writing about. Okay. So it burned. We don't know if the person hasn't seen the question, they don't know what it is. Okay. I'm trying to get you guys to start writing more scientifically. The magnesium burned, creating magnesium oxide. That would be something that somebody who hasn't seen the question will be able to understand. Does that make sense? The difference as opposed to it burned. All right. Any other questions on the lab? Did that help clarify a few things on there for you? I hope. All right. So then I want to turn our attention over to our chapter review. I have on here, and this review answer key is already, well, after this video, 3rd hour gets uploaded, this answer key will be on Google Classroom for you. Okay. I believe I also put it on there last night as well in yesterday's post, but I wouldn't swear to that one. Do you remember? Did you see? Okay. Okay. Well, it's already on the post. I just have it saved as a draft. So as soon as I get the video going, then get it uploaded to YouTube, then it'll be out there, and I'll try to get that done 3rd hour. All right. So if you don't want to spend time writing all these definitions out, if you want to create some flashcards, whatever, however you want to study for this, I am not taking this review for a grade. Okay. So you do whatever you need to do. If you already know this stuff, great. Okay. Don't waste your time writing definitions down that you don't need. All right. Examples between extensive and intensive. Remember that extensive, if we add extra, that is going to make a difference. So yesterday, for example, we had our lab. In that lab, we had extensive properties that we were using. What is an example of an extensive property from lab yesterday? Mass, okay? If we would have had a bigger piece of magnesium, the mass would have been different, okay? So that's an extensive property. Intensive property, then, it doesn't change depending on how much you have. So for example, yesterday, an intensive property could have been the gray powder inside, or the gray residue inside that. That color wouldn't have changed if we would have had a bigger piece of magnesium, right? And we reacted it, it would have just been the same. All right. There are two most common properties of matter, which are mass and volume. We ratio those together, and what do we have? The ratio of mass. Yes. Then we have density. Okay. We talked about definitions as far as atoms, compounds. Remember, atoms, if we were to do a particle diagram, we would just have one, or we might have two at the most bound together. Okay. Remember, these are called diatomics. That definition will not be on your test. I'm just explaining it to you. Okay. So diatomic molecules, you might have two together. You would never have three. And I ended up having people tell me that 3 yesterday was an element on your lab that you turned in. So keep in mind that this is not an element. That would be a compound. So at most, you would have 2 that look like this in the diagram. As far as a compound is concerned, we had examples on your sheet that were like this. We had a couple that looked like this. Those would be compounds, okay? They're connected together. This then, if we had all of this in a container, this would actually be a mixture because they're 2 different compounds in there. And they're not chemically bound together. This won't let me erase like that. Okay. If I had a drawing that looked like this, though, and this was all in the same container, that would then be a what? Why is that not? I try to get this stuff to work. This and this should look alike. I just can't get rid of that square box. What would this be called then? What is this? Compound. And how I have both the same thing, so this is just a compound. Okay? Makes sense? All right. Examples of matter.
Any juniors with the last name from G to R who still need your picture taken or retaken should head to the small auditorium at this time. Again, any juniors, last name G to R, need your picture taken or retaken, you should head to the small aud at this time.
All right. Examples of matter then: air, smoke, water vapor. Examples of non-matter will be like light or radio waves. Chemical changes then, they always change the identity of the substance. So burning, leaves changing color, rusting, those sorts of things. Physical change then does not change the identity. So when we heated that wire rod, it was still a wire rod when you pulled it back out of the Bunsen burner. Your crucible itself, the metal of the crucible, when you just heated that by itself, that was just a physical change. It increased the temperature of the item, but it still remained a crucible. Okay. Grinding, cutting, we had a bunch of different examples of those. Remember, all phase changes are physical changes: boiling, melting, freezing, sublimation, deposition, vaporization. All of those phase changes are physical changes. Noble gases do not react. They are the last column on the periodic table, and they got their name because the nobility don't interact with the commoners. Reactants are the things that start in a chemical reaction, and the products are the things that are formed. These double ticks here, these are called ticks. That means that whatever was written up here gets brought back down here. So you don't have to rewrite it. It's a faster way. It's just a way to annotate something faster. Okay. All right. When we talk about solids, liquids, and gases, our solids have a definite shape and volume. Our liquids take the volume of the container, so we say that they're variable. The volume then is going to be definite, and then gases, they're both variable. They take the shape and volume of their container. What happens when matter changes state? It's going to change forms, but it's not created or destroyed. During a phase change, the temperature stays the same. This is heterogeneous. We have some large particles. We have some small particles, different size particles. This is homogeneous. This is a mixture. This would be a mixture of what? Elements. These are not bound to another thing. This would be a mixture of compound and elements. So this is an element. This is an element. These are different compounds. So you've got different elements and compounds in here. So this would be a mixture of elements and compounds. This would just be elements. This, I could argue, either is heterogeneous or homogeneous. Now, homogeneous in terms of size, heterogeneous in terms of the fact that they're separated out into two layers. Okay, so this could be like oil and water, for example. Okay, you're not going to have to tell me the difference in a particle diagram between homogeneous and heterogeneous. You just have to tell me if it's a mixture or not. If it's a mixture, compound, or element. That's all you have to do. You don't have to tell me what type. Homogeneous mixtures then are called solutions. Where are they located? They're located, the periods are located and groups are located in the columns, so they run up and down. The rows then are going to be your periods, and they are going to run across. Good characteristics of metals. They are good conductors of heat and electricity. They're ductile, meaning that we can draw them out into thin wires. And they're malleable, which means that we can pound into thin sheets. Nonmetals then are brittle and hard. Metalloids are known as the semiconductors. And remember, on our periodic table, they are located by that stair step. So we have a stair step over here, which divides your metals and nonmetals. Your semiconductors then are found by that stair step. The next part here then, if we have 9 grams of A combining with 18B, how many grams of AB would we expect? We just have to add those together to get our whole. Okay, questions on any of the stuff that I've talked about so far? The material that I just presented in the review will be contained in 18 multiple choice questions tomorrow. So there's 18 multiple choice questions about that material. There's no math from that section that you wouldn't have an answer for already. Okay, so all of that is going to be multiple choice. Questions about that? All right. The next section then, oh wait, nope, I lied. That is not, we still have this stuff. So I'm going to pull 18 questions from this stuff. This is still on there. This is down here. This is where we start the written portion. Okay, so I still have another page to go through. So some of this stuff could appear in the 18 questions tomorrow. I apologize for my misdirection there. All right, we have 26.4 grams of copper, 19 grams of oxygen. It's going to make copper oxide. They want to know how many grams of oxygen would be needed if we combined that to form CuO2. Well, here they're in a 1-to-1 ratio. Okay. If I double this amount, then I would have to double this second value. So it would be 38 grams. Is that making sense? I had it in a 1-to-1. Now I got it in a 1-to-2. All right, pure substances have fixed ratios and definite proportions. Remember, our mixtures are going to vary. We have 2 categories of pure substances, which are compounds and elements. Examples of those then would be mercury, aluminum, brass, water, salt. These are all compounds down here. These are your elements. Remember, there's a good listing of those, which is a periodic table. You will have a periodic table to use on your test. You do not ever need to memorize anything on the periodic table in here. You will naturally, over the course of the year, start to memorize some of them just because you use some of the stuff a lot, but you don't have to. It's not an expectation. What is a mixture? It's a physical combination of 2 or more substances. Characteristic of a mixture, we can separate that by physical means. So physical means would be like, we talked in class about distillation. We talked about chromatography. We talked about crystallization. We talked about just picking things out manually. Filtration. So there's lots of things that we can use physical means to change that mixture or separate it. 2 classifications mixtures then are homogeneous and heterogeneous, and I've given you a listing of some examples with those. Remember, solutions is a synonym for homogeneous. Does heating always cause a chemical change? No. Your crucible yesterday, for example, okay? We heated that crucible. It was still a crucible when we got done, wasn't it? Okay. The wire rod a couple of days ago, we heated the wire rod. It was still a wire rod when you were done, yes? Okay. All right, this is the math portion. Okay, you are going to have, if I pulled out the test right now, you would be hard pressed to be able to tell the difference between this page of the review and the test. Okay. You are going to have a chart identical to this chart. Okay. You've got the mass of the sample over here, and then you've got your 2 components. These are your parts. This is your whole. So to figure out the percentage, you do the part divided by the whole. Now here, we didn't give you the whole. How did you figure it out? Yeah, we added the 2 parts together to get the whole. Here we gave you the whole and we gave you one of the parts. How did you find out the other part? Subtract it. Okay. And then for all of these, it's just the part divided by the whole. They're asking you here if any of the samples are the same ones. Well, if none of these masses percents match, they're not the same ones. Chemist here was looking to see if the compound was 66.6% A and 33.3 B. Did they find that? No, there are none of these that match up to that value. Here we have zinc combining with fluorine. They want to know how many of this. This is a law of conservation of mass. If you start out with 2 parts, The final result has to be the same mass. Here is just another one of those other questions. You got 95 grams of X. It's combining with 8 grams of Y to form XY. This is in a 1-to-1 ratio. Here you had 95, and here you had 8. Over here, we're going to be forming XY2. So this is going to be in a 1-to-2 ratio. So if this is 95, what do I have to do to this 8? Times 2. Okay, the ratios went from 1 to 1 to 1 to 2. I just need to multiply that value by 2. And that's where we got the 16 grams. All right. This question here, we have a sample of mercury oxide. It's 7% oxygen. This says oxygen, you guys. Okay. They want to know how many grams of mercury are there. So first of all, I need to figure out my percent mercury. Well, if it's 2 components and one of them are 7%, the other one has to be 93%. So if I have my total here, I can multiply that by this out of percent form, and that's going to give me my grams of mercury. Should this answer be larger ever? Should your answer of one of the parts ever be larger than the whole? If it is, you goofed. And then you've got a last problem down here. It's going to be a compound. It's probably going to have a parentheses with it. So you need to make sure that you know how to multiply through parentheses. Malachi, are you comfortable with these now? How to do them? Okay. Where did I get these values from? Periodic table. Where did I get these values from? The subscripts. Okay. Where did I get this value from? I added all the parts up after they had been multiplied. Okay. That is the test. Are you feeling okay about it? If you're not, come in and see me tomorrow morning, okay? So I can help you through some stuff. I'll be here bright and early. If you want to come in earlier than 7:15, let me know tonight so I can email Miss Jones to let you in early, okay? You have to come in door 1 if you want to get in early, okay? And you have to let me know so I can let her page you in. Good? Any questions for me? Anything you want to talk about? I've still got a couple minutes. I think we get out at 39, right? No. Yeah, 39 today. Everything keeps changing.